Okay, welcome to today's seminar. It is in the field of solar physics. We have with us Angelos Michailidis, who recently was in our group working with Kostis Gondikakis. Kostis will make an introduction and then we continue with the talk.
Good day from me too. Just a few words for Angelos Michailidis. He graduated from the University of Ioannina in 23, where he did his diploma on solar physics on coronal dimming, and then he did his master in the University of Athens, and the diploma of the master was done here at the Research Center of the Astronomy and Applied Mathematics with a subject on the solar jets. In 25, and now he started his PhD at the University of Ioannina under the supervision of Vasilis Archoldis.
Good morning, everybody. Dr. Godikakis and Dr. Patsis, thank you for inviting me today and giving me the opportunity to share my work with you. I'm very happy to be back here to see familiar faces, friends, and colleagues. As you can see from the title, today I'm going to talk to you about the solar wind and how we believe that the solar wind is formed, which might be jets, as we're going to discuss. A brief outline. As I understand, not everybody in this room is a solar physicist, so I'm going through a brief introduction to define some terminology to make sure we're all on the same page. Then we have two components for this talk, solar wind and jets. So I will discuss a few things about them both. And then we're going through the observational indications at first that the latter is the driver of the former, and we also have some numerical data to support this idea. And finally, we will summarize and we will draw our conclusions. So the key topics that I'm about to discuss in this talk are the concept of interchange reconnection, something known as the differential emission measure, the first ionization potential effect at the upper solar atmosphere, and what is thought to be its driver, the model of the ponderomotive force. So let's begin. I already said the word solar atmosphere a couple of times, so let's define what it is. Generally speaking, the atmosphere of the star is the region from which we can receive electromagnetic radiation. And regarding the solar atmosphere, it is stratified in layers, starting from the bottom, going all the way to space. We have the photosphere, the chromosphere, the transition region, and the corona. So the photosphere is essentially what we know as the sun, what we see up in the sky. It is the brightest layer and is essentially the solar disk. Then above it lies the chromosphere. Chroma is the Greek color for the Greek word for color, and this because of the red color of the hydrogen emission line that we observe. The photosphere is very bright, so we're not able to observe it directly. We need to use special equipment or in the occasion of a solar eclipse. Then the outer layer, the corona, which is Latin for crown, this because it appears like a bright crown around the solar disk. Once again, because the photosphere is too bright, we cannot observe it directly, so we need a special equipment, an instrument known as a coronagraph, that blocks the photospheric emission and allows us to observe the corona. And as you can see in this plot, between the chromosphere and the corona, there is a transition region, a short transition region, where the temperature of the atmosphere rises rapidly 2 orders of magnitude. This is a phenomenon that is not still understood completely, but the fact that it happens will be important later on. This was a one-dimensional description of the atmosphere, but we also have texture. So we have active regions. These are regions where we have enhanced magnetic flux. Then we have quiet sun. These are regions with minimal magnetic flux. And when we say the word quiet, it's not really quiet in the sense that nothing happens there at all. It's just that these regions aren't as active as the active regions. And then we have coronal holes. These are regions where we have open magnetic field configurations. Plasma can escape through these magnetic fields and therefore leaving behind a density void, which looks like a hole. How do we measure those magnetic fields on the sun? We use the Zeeman effect. So let's say we have a spectral line due to an atomic transition. Because of the presence of an external magnetic field, we're going to have like a splitting of this spectral line into two, let's call them wing components. I don't know if this is the appropriate term, but just for the sake of it. So this separation is proportional to the applied magnetic field. One can measure it and therefore measure the magnetic field. However, this is not as straightforward as it might seem. However, we are lucky, fortunately, because those components are also polarized accordingly to the applied magnetic field. So it's way easier to measure this polarization. And this allows us to construct maps of the magnetic field on the solar surface known as magnetograms, like this one, for example. Unfortunately, this can only be done for the lower atmosphere, the photosphere, because in the upper atmosphere there aren't any spectral lines that are appropriate to do this job. So what we do is that we take photospheric magnetograms and we extrapolate them up to the corona. A very common way to do this is to consider the state of equilibrium, and therefore the J cross B term equals 0. J is the current density and B is the magnetic field. And two things are implied by this condition. Either there is no current density at all, or the current density is parallel to the field. In the first case, if we substitute that in Ampere's law, then we get that the curl of the magnetic field is 0, and we know from vector calculus that such a vector field can be expressed as the gradient of a potential field. Let's call it psi. So this is the potential extrapolation. If we take the more general case where we have a current density parallel to the field, then we can express this current density as the magnetic field multiplied by a scalar function, let's call it alpha. And if we substitute that to Ampere's law, we get this equation in that box. If we consider that this scalar function is constant in space, then this is a linear equation, and we have the linear extrapolation. And the more general case, we do the same as above, but we don't have to consider that this function is constant in space. However, one can prove that it has to be constant for its magnetic line. For our purposes, we have worked with the first extrapolation, which is the simplest one, but also the one that suffers the most. And we have used what is known as the potential field source surface model in order to do this extrapolation. And what we do there is that we solve the potential case inside the spherical cell. The inner boundary is a photospheric magnetogram, and the outer boundary is a spherical surface with a radius of 2.5 solar radii. This is because at this distance we know from observations that the field should be radial. This is our geometry. So the solid circle is the photosphere, and we have our photospheric magnetogram. And this dust circle is the source surface. Outside there, the magnetic field is trivial. It's an Archimedes spiral. At this point, it is radial. So we solve this equation inside this region. How do we do that? We begin with Gauss's law for magnetism. We substitute our condition for our potential field, and this yields a Laplace's equation that we solve in this geometry. We do this numerically using the PFSS-Pi package for Python. What we do is that we solve the equation in this numerical grid, and we apply the method of variable separation. So we assume that our solution for this potential is a pure radial part and a pure angular part, and also we choose the angular part to be the spherical harmonics. So this is like expanding the solution in the base of the spherical harmonics. Then we apply our boundary conditions, and after we do that, we have eigenvalue problems to solve. So the n mode is for longitude, the n mode is for latitude, and essentially what we do is that we cut our grid into m slices, and we solve an eigenvalue problem for n for each m slice. And this reconstructs our field. Okay, a little bit more with the technical stuff. Now let's discuss what is the differential emission measure, or DEM for short, which is a distribution of the density of the plasma over its temperature. So let's consider a plasma layer that emits some spectral lines in the ultraviolet part of the spectrum. And this emission is optically thin. That is that the average photon can pass through this plasma layer without being scattered or absorbed. And such a plasma layer is, for example, the transition region of our sun. One can prove that the intensity of this emission is proportional to the square of the electron density of this plasma. And regarding the temperature, we can describe that through a contribution function of temperature, because the ions that emit those spectral lines are formed in a specific temperature ranges. Taking all this into account, we can express the intensity of these spectral lines as in equation 9, where we integrate the square of the density and the contribution function over temperature and over the length of the plasma, T and L respectively. And so if we define the differential emission measure like the square of the density dl over dt, and you can see how this is a distribution of the density over the temperature, we can rewrite equation 9 as equation 10. And this is a very beautiful equation, because what it tells us is that given the atomic physics of the emitting plasma, which is expressed through the contribution function, and given the physical conditions of the emitting plasma, which are expressed through the DEM, you can calculate the intensity of this emission. Which is great, isn't it? Well, it isn't, because there's a problem. In this equation, what we actually know is the result of this integral, because we measure it with our telescopes. We know the contribution functions from calculations in atomic physics, and thank you, atomic physicists, for doing this work and providing the databases to us to work with. And what we wish to recover are the physical conditions of this emitting plasma, which is the differential emission measure. But there's a problem, because this is inside the integral. This is known as an inversion problem, and generally speaking, it's very hard to solve. One way to do this is to discretize this integral and write it like a linear system. And so we choose a set of spectral lines in the ultraviolet part of the spectrum that are formed in a temperature range. We write it as a linear system, and we try to solve for the differential emission measure. However, there are only so many. Excuse me.
Is it obvious why the differential emission measure is a function of temperature only, and the density is a function of temperature?
You mean here? Yeah, it's in sense.
This contains the density square. That's a function of temperature.
Yeah, so essentially what the differential emission measure is how much density lies in each temperature, if that makes sense. If that makes any sense, it's like a distribution of density over temperature. And when we, substitute and there are some things that cancel out with each other, and then this is an integral of temperature, if that makes any sense.
It's not a bit, it doesn't depend on position, or?
No, because we don't do it spatially. It's like we have a column for this emitting plasma, and we want to know, the how much density lies for each temperature. For example, for each temperature, we have that density. For the other temperature, we have that other density.
We have integrated over the position and all the other.
Yes, we have integrated over the length of the plasma
All the
layer.
other parameters we have integrated.
Yes, yes, exactly. That's true.
DL is the thickness of the layer.
Yes, it's the thickness of the layer, DL. That makes sense to you?
When you say position, you can make maps of the on the sun. Maps, like an image.
Okay, you have a DL there,
Mm-hmm.
and you integrate over the temperature in that DL at that position. So there are many temperatures at that position.
The key thing there is that we have an optically thin emission. So
So you're seeing all the atmosphere.
exactly, we receive a radiation from the entire.
There's no integral over DL then?
What we imply here is that when integrating this thing over the entire length of the emitting plasma, that's what we get, because we have an optically thin emission, so we receive radiation from the entire plasma, and so we only have information about the temperature.
So the intensity one should expect to be an integral over DL over the distance from every part along your line of sight. You have contribution,
Mm-hmm.
and yet you took the DL out and you integrate over temperature.
Yes, I mean, you're right in that way, that this for the entire plasma.
Yes, because the length, the L can be very small and introducing a large range of temperatures. So you prefer to have the quantity of integration to be the temperature.
So the true integral should have been an integral over DL integrator over the full length, not DL, the full 1.5 stellar radii or something in this, the whole atmosphere in some sense.
No.
And then that integral, you rewrite it in that form as if you were integrating over T, over the temperature.
I'm not exactly sure that I understood.
In fact, you integrate a small range of the temperature when you small range of the length along the line of sight, where the temperature changes from 200,000 Kelvin up to 1 million.
Okay, so this is a specific application in the transitional region then.
Well, it is used there because there you are optically thin. The lower atmosphere you're optically thick, so you cannot include it. And there you have many spectral lines formed at different temperatures.
In general, the integral should have been over DL. But the way you're saying it now, it's a very thin region, so DL is small, that contains all these very many temperatures. Because it's a transition region and very quickly things change. So you cannot distinguish that in space. And that's why you integrate over temperature.
But basically it is over DL because
Yes.
it's just a variable transformation. If you cancel out the temperature, the difference of the temperatures, only DL remains.
The quantity that
DL is fixed, it's a few thousand kilometers.
The quantity that is known in astronomy is an emission measure. Square density times length.
Yes.
But now you want to express the fact that you have many temperatures, plasma quantities in
So
different
exactly, that's my point.
Mhm.
So the emission measure is square temperature density times length. And you, in general, you integrate over length.
Yes,
That's how you do that.
Yes, this is for the entire plasma.
For the entire plasma. But in this particular region, for a very small length DL, the transition region is very narrow, you have many temperatures. And you transform the integration over length to an integration over the temperature.
Yes, that's pretty much the idea. That we have a small layer with several temperatures in it, and we get contributions from all those temperatures, and we want to know essentially how much each temperature is contributing to this emission.
So this is why I said first that the density is not really a function of temperature, it's a function of position of L. but you transform it as
Okay,
being a
yes,
function of
yes.
temperature.
Now I understand what you say. Yes, exactly, because this is due to the temperature profile. Yeah, we can somehow transform the position to temperature in height because at the beginning I showed the temperature profile. There it was. So yeah, we have a very short layer there,
Yes.
but it has all these temperatures in it. And because of the temperature profile, yes, we can like transform the position to temperature.
But it has all these temperatures and it also has all these densities. If you were to plot the density, it should very quickly drop to a very low value in that region.
Yes, that's true. And so this is how we know how much its temperature contributes to our emission.
I'm saying it's a strange way to showing the intensity is usually an integral over the path of the photon, not over the temperature.
Yes, I implied that, but I didn't present it. Maybe.
But in the transition region, you
Yes, this is the reason, and thank you for pointing it out. Okay, where was I? This is now we have as I was saying before, we discretize equation 10. We write it as a linear system, but this is an ill-posed problem because we have a limited set of spectral lines, but so many temperatures. So in theory, there are infinite solutions, and therefore we need to solve via regularization in order to obtain a unique and physical solution. One more thing about the technical stuff. There is a phenomenon known as the first ionization potential effect or bias. And this is that in the upper atmosphere, in the coronal and the transition region, for example, there are elements with enhanced abundances that have a low first ionization potential. And their abundance is enhanced compared to those elements with high first ionization potential, or FIP for short. The threshold is 10 eV. We define this bias as the abundance of an element in the upper atmosphere over its abundance in the photosphere, but we mostly care about the relative bias, which is the bias of a low FIP element over the bias of a high FIP element. And the driver behind this is thought to be the ponderomotive force. So let's take a closer look. Let's say here that we have a magnetic loop that has its foot points in the lower atmosphere, in the photosphere and the chromosphere, and extends all the way up to the corona. And so what happens here, remember the temperature profile. The temperature there is 2 orders of magnitude less than what it is here, for example. So only the low FIP elements are ionized. Then we have some electromagnetic forces, for example, from alpha n waves, that act upon those ions and accelerate them through this magnetic loop. So only the low FIP ions are affected by those forces and they get concentrated in this magnetic loop. But had that been an open field, then those ions would escape and the phenomenon would be undone. So what happens is that in active regions, that the field is mostly composed of those loops, we have an enhanced, we can measure this bias, while in coronal holes, we don't. We have the photospheric abundances. And this, again, will be important later on. And how do we measure this bias? We need a spectral line from the low FIP element and a spectral line from the high FIP element. And it would be very useful for us if those spectral lines form in similar temperatures. But we also need the contribution functions and the differential emission measure. That's why I included the previous slide in order to take the exact contribution of this emission of these abundances. And this is how we can measure this bias. But we can approximate equation 13 with equation 14 if we have 2 spectral lines that form in similar temperatures, and we also consider an isothermal emission, so the DEM gets eliminated, and this is a good approximation of equation 13 under those circumstances. Okay, that's with the technical stuff. I haven't entitled the word solar wind, so let's see what this is. it is a continuous flow of plasma from the sun's upper atmosphere to space. It was predicted in the 1950s by the great solar physicist Parker, and a few years later, it was observed in situ measurements from space-based satellites at the beginning of the space era. Since then, we understand that there are two components of solar wind, the slow and the fast. The slow originating from the active regions and having a speed range from 250 to 400 kilometers per second, while the fast wind originates from the coronal holes. It's less dense and they vary in composition. And the important thing is what I said before about the abundances, that we observe this FIP effect in the slow wind, but the fast wind has more photospheric abundances. We understand how the solar wind flows in speed, but we don't really understand that well its origin. And there have been some studies that suggest that the origin of this wind might be jets in the solar atmosphere. These authors, for example, all these authors, for example, or the most recent paper about this matter by these authors, all those papers suggest that jets can contribute significantly to the solar wind. So jets are collimated plasma beams in the atmosphere. They come in all sizes. They can be a few hundred meters long to several solar radii long. They may occur anywhere in the solar atmosphere. As I said before, they're thought to be a source of solar wind and also coronal heating, as they can transfer mass and energy flux from the lower atmosphere to the upper atmosphere. And their driver is the mechanism of magnetic reconnection. Yes?
Another question.
Please.
You said the solar wind from the active regions from the coronal holes.
Mm-hmm.
But the solar wind originates in coronal holes, in open regions.
No,
By
not.
definition.
No, it's not by definition, and I will discuss this later. I will.
So meaning that it lives forever. Coronal holes live forever. Active regions are closed. You said that.
I said that.
So how can the solar wind originate from a closed line region?
The solar wind from those active regions is the result of reconnection. That's the entire point of those studies, that we have reconnection occurring there that give rise to the solar wind. So morphologically, we can classify jets into two categories. What is known in literature as anemone jets, or lambda jets, or inverted Y jets, like the one on the left, and the two-sided loop jets, like those on the right. When we observe them all the way up to the corona, then we call them coronal jets. Those jets, of course, have are very long, so several solar radii. Once again, they may occur anywhere. They may be equatorial or polar, but the most important thing, and this links to your question, they seem to originate from either coronal holes or, most importantly, at the boundary of an active region with a coronal hole. And this is a region where it favors a mechanism known in the literature as foot point reconnection or interchange reconnection. But before I discuss that, I want to take one slide to discuss how we observe those things, because in a coronagraph's field of view, there are several structures that we might observe. For example, there are streamers, there are pseudo-streamers, there are coronal plumes. So how can we tell which one is a jet? The trick, let's call it, is that we take a difference image, that is, we take two successive images and we subtract one from the other. And all these structures are quasi-static apart from the jets, so they are eliminated in these difference images, and this is how we can distinguish the real jets. And regarding the interchange reconnection, this occurs when we have a magnetic loop neighboring an open field, and the foot points of the loop have different opposite polarities to the open lines, and therefore they reconnect. giving rise to those jets. This is how we believe these are generated. Okay, that's good in theory, but do we actually see those things? Yes, we do. We see them in extreme ultraviolet observations. This is emission from the upper atmosphere, the transition region and the corona. Of course, we see them in coronagraph observations. I already showed you some examples. We can study the interchange reconnection with magnetic field extrapolations. Regarding the abundances, we use spectral data to study the FIP effect. And of course, for the solar wind, we have in-situ measurements from space-based instruments. We have studied 2 examples so far, and there are more to follow. This is active region 12957, and we studied from March the 3rd until March the 7th, 2022. This active region that you see here neighbors a coronal hole. I just haven't included that because it wouldn't fit into the frame, but about there is a coronal hole. And this is, for example, one jet that was observed on March the 3rd. You see there the collimated plasma beam. And this is a fainter one. This projector doesn't help, but I can see it clearly in this little screen. On March the 7th. So for this jet, it happened when this active region was close to the center of the disk. So it was not projected in the coronagraphs. But March the 7th, this active region was closer to the limb. So it was projected to the field of view of the coronagraphs. This is the solution of the potential extrapolation. With white color, we have the closed loops, and with blue colors, we have plotted the open lines. And you can see how we have this configuration that I talked about, the combination of loops and open lines that favor this interchange reconnection. And this is an image from a coronagraph in polar projection. So the x-axis is what is known as position angle. We begin from the North Pole and we go counterclockwise. And the y-axis is something equivalent to radial distance. And we can see, again, in this projector is not that clear, but we can see the ejection of this jet as the result of this reconnection. I have here the evolution of the event from 2 coronagraphs, from Sohos-Lasko C2 and from Stereo A Core 2. So these are the same phenomena observed from 2 different points in space. You can see the time evolution of it. Actually, once again, this projector doesn't help, but I can see it in my screen. And because we observed this phenomenon from 2 different points in space, we were able to recover its 3D geometry through an algorithm called triangulation, which was performed by Dr. Rusan of the Observatory of Naples. And in this table, I have summarized the 3D geometry of this event. Okay, this is just to showcase that we are able to do these things and know exactly how the events that we study, we can recover their geometry. Okay, these observations are fine, but how are they connected to the solar wind? They are, because otherwise, why would we be here today? So let's remind ourselves of the FIP effect. And this is, the closed loop that I talked before, the temperature profile. And because of the ponderomotive force, this loop has a strong bias, while the open field next to it doesn't have that bias. And so what happens when they reconnect is that this loop, through the reconnection process, transfers its bias to these open lines nearby, and therefore to the solar wind. And this is how we can explain that the slow wind has this bias, because it is the result of this reconnection, while the fast wind doesn't have this bias. And so we have measured it. using the method that I have showed. This is we have what are those images? Let's discuss what are those images. These are maps of this FIP effect. This map is by the full DEM method, and this map is produced with the two-line approximation. What we see on the top is the product of the contribution function of the elements that we have used, which are magnesium for the low FIB and neon for the high FIB. With the DEM, it's the product of the contribution function with the DEM. And we have done it for regions of the magnetic field that are closed and for regions with open magnetic field. I think the colors are not clear there. Maybe they are in the small screen. But we see how these emissions of these two elements are more or less in the same temperature. Actually, if we take the approximation, it's essentially the same as taking the entire thing, because this is only, the region, the temperature range of the contribution of the emission that contributes the most. Okay, so this is the active region on March the 3rd, and those spectral data were obtained from Solar Orbiter's spectrograph SPICE, and this is where we got the jet, and this is the loops that we have in this active region. We see that the loops have a bias of 2 to 3 to 4, which is consistent with what we find in the literature, and especially there that we have this jet, we see a very strong bias. So this is how we can make this connection. Is this enough? Yes?
We have a lot of what bias means. We understand that it means you have closed lines and you connect one to the other, and you have the.
Okay, so the bias is that the low FIP abundances are enhanced compared to the high FIP abundances. Because here we have the low FIP elements that get ionized and accelerated and transferred in this loop. But when we have open field, this doesn't happen. They escape and the phenomenon is undone. So we can measure this thing and see that the abundance of the low FIP element is enhanced compared to the abundance of the high FIP element.
So does this FIP effect, I don't understand it. Does this have to do with open and closed lines? Tell you where they have coronal holes and where you have closed lines?
Yes, it is correlated because it's correlated. In the closed loops, we have a strong bias, and in the open fields, we don't have it. It's photospheric emission.
At the same time, I think along open lines, you have lower temperatures also. It's another effect, or not?
No, I'm not aware of that.
Coronal holes are colder. They seem darker in the image.
This due to density. The emission is proportional to density. They look darker because we have a density void there. And the emission in the EUV part of the spectrum is proportional to density.
The emission top, you see the same regions there?
Yes, I have it there. This, for example, this is the emission, and in the closed fields where we have greater densities, we have also stronger emission in the UV part of the spectrum.
Do we learn anything more from this FIP effect that you mentioned?
Yes. First of all, it is an observational verification, let's call it, of the model that this actually happens. We can measure it, and we see that this is what really happens there. And then we know that the slow wind carries this FIP bias with it, and we show that if all these models were true, how should I put this? We can trace this back from the solar wind to the solar atmosphere through this effect and make a connection. This is the idea, that this is how we make the connection from the solar wind to the solar atmosphere through this effect. I hope that answers your question. I have just included both calculations to see that because we get contributions from the same temperature range, we can use this approximation and get almost identical results. And yeah, we can see how strong this effect, this FIP effect is on the region where we get the jet. And this is carried all the way out to the solar wind. And this is how we can make this connection observationally. Is this enough? Maybe it is, maybe it's not. We also have numerical data to support this idea. The team of the University of Ioannina that I currently am a member of, they run simulations using the LR3D code. They run simulations of the solar atmosphere. And what they do is that they create magnetic flux tubes, for example, a horizontal tube or a toroidal tube or other configurations. They emerge, they reconnect with the ambient field, and they give us phenomena such as those that we observe in the EUV data. What I do with those simulations, I'm not the one who makes those simulations, but I take those simulations and I try to measure the mass and the Poynting flux of those events and compare it to data from observations that you can find in the literature. There are some reference values, and I try to compare those fluxes and see if those jets can support the flux of the mass and energy of the solar wind. I have some results to show you actually, but we made a decision to not include them in this presentation because this is a work still in progress, and we decided that once it is fully completed and submitted, then we will share our results. However, there are other teams that do similar work to ours. And this, for example, from these authors, they have a simulation where they use a dynamo magnetic field to produce those jets, and they measure the mass and Poynting flux in several heights in their simulations. And so what they measure here is mass flux on the top plot and energy flux on the bottom plot, and they compare to those reference values, and they show that these measurements are in the same order of magnitude, and therefore they conclude that this mechanism can sustain the solar wind.
The slow solar.
Yeah, the wind that is thought to be due to interchange reconnection. They show that this mechanism is sufficient. Actually, it's not that straightforward because we simulate such an event, and then we need to apply some normalization. For example, how many events do they occur per day? How many do we have, in the entire sun? And we have to take those things into account to make a strong argument. But so far, all the observational and numerical indications that I have worked with support this idea. So let's summarize. We have seen so far that those jets that are produced through the mechanism of interchange reconnection are consistent with our models. We can model them, and then we can observe them, and we can therefore verify that this is the mechanism. We can measure the abundances and make a connection of the abundance of the solar wind with the abundance of the jets at the atmosphere that we think is the origin of the solar wind. And on top of that, we have also numerical simulations that suggests that the mass and energy flux of the solar wind can be sustained by such events. So some acknowledgements there. And thank you for your attention, and I look forward to your questions.
Also, thank you very much for the nice presentation. There was some discussion of.
How about the fast wind?
The fast wind, as far as I know, is described like what Parker did in his work with his MHD work. It's not a perfect Parker wind, but it's more close to what Parker had predicted in the 1950s with his MHD approximations. But the slow wind is the hard thing to understand. There are some papers in the literature that suggest that the distinction should be made not based on the speeds, but based on the abundances. And what we actually call slow wind, we should actually classify it according to its abundance in low FIP elements. So yeah, this fast wind is more or less understood at some extent, or at least a lot better understood than is the slow wind with Parker's model, the MHD model of Parker.
So what accelerates the fast wind?
Yeah, I'm not aware of that, but yeah, this is a good question actually.
But if these are like Athens waves and things like that, and
Yeah,
and reconnection, micro reconnection, why doesn't the same thing happen in the slow wave too?
Yeah, to be honest, this work really included the slow wind, so I'm not sure I can answer all these very good questions regarding the fast wind. Yeah, to be.
So it is very interesting that
It is.
you found one effect, this jet formation effect, and you managed, or the other people managed to account for the full slow wind with this effect.
Mhm.
This is very so, as if nothing else contributes to it. And in the fast wind, there are theories of what contributes and produces the fast
Mhm.
wind. It's interesting that
There are also
this
jet-
one effect managed to accelerate.
There are jets also inside coronal holes. So you also could have jets affecting also the coronal hole solar wind. You also has
From the foot points.
Yeah, I mean it's it's a very complicated phenomenon. I assume that there are papers, there are articles in the literature that discuss those things. It's just that it was out of the scope of my work because my work was focused on studying those reconnection effects of loops at the active regions with the neighboring coronal holes. So this is the literature that I mostly focused on.
Thank you very much for your talk. I haven't really understood which is the relation between jets and CMEs, and which is the phenomenon that is responsible for geomagnetic storms on Earth in order to study for the space weather.
Okay, yes, that's a very good question actually. They're both the result of magnetic reconnection. From what I'm aware of, it's a matter of scale because the CME is a very large scale phenomenon, and while the jets are more localized, there are some events that are at the boundary of being a very wide jet or a very narrow coronal mass ejection. So yeah, it's not that there is a clear boundary that separates them, more like I don't know, a range, shall I call it? But yeah, it is magnetic reconnection and they differ in scale for the first part of your question. As for the second part of your question about the geo-effectiveness of CMEs, yeah, this is the magnetic field carried by the CME as it propagates through space. And when it hits Earth, if it is appropriately aligned, that is, if it the magnetic field of the CME points towards the south, then it can reconnect with the Earth's magnetic field and therefore be geoeffective.
How often does these effects happen on jets and CMEs?
CMEs and jets happen all the time.
All the time.
They are very common. A CME hitting Earth, it's not as common as a CME just occurring, because it has to be aligned with us. But CMEs happen all the time. They're very common, and so are jets.
The quantity of plasma is very important for the geomagnetic storm, the quantity of the plasma.
From what I know, because this is not really what I study in my master's and my PhD, but as far as I know, the most important thing for it to be G-effective is the magnetic field that it carries, so that it can reconnect with our planet's magnetic field. I think the pressure also is important, but this is not the field of my expertise, so better not answer things that I'm not an expert on.
Just about this simulation that you show at the end, and the one published by Peter, are they in the context of an active region or white sun? Does there is such a distinguish this?
Yeah, so I think they try to simulate active regions because they have magnetic fluxes emerging in our simulations. They have this magnetic field dynamo in their simulation. Yes.
They could be also on a smaller scale in white sun.
Yeah, that could be. But these are phenomena that for the interchange reconnection to occur, for them to be realistic, this is where they happen.
No other questions in the room. Let me check if we have any questions from those who follow. Yes. If anyone has any question from those that you are online, please go on and ask. Okay. Don't see any reaction. So thank you again.
Okay.